Hey guys, this is Mrs. Gebhardt, and this is the notes on relative versus absolute age. So as you get your fill in the blanks, you should be putting in all the answers as we go through it. The following questions you need to be able to answer at the end of this note set. First, how can the amount of apparent material in a rock sample be determined by using half-lives? Second, how does the amount of apparent material in a sample change as time increases? And third, how does age of rock at the bottom of a rock formation compare to that of a rock at the top of a rock formation? So the first term we come across is something called relative dating, and this is often used in geology to determine the order of events in relation to other events. So for example, if you were at your house and I were to ask you how old your siblings are, you could tell me that you have a sibling that's older than you are or younger than you are. You don't have to necessarily tell me their age. So telling me that they are older than you, I kind of have an idea of how old they are because of the relation to you. This is also known as the law of superposition, and this doesn't say anything about the exact age of that rock layer, so make sure we get that clear. All this tells us is whether that rock is older or younger. We don't know how old the rock is in years, or any fossils that could be found in that rock. We also don't know how old they are. This will often work best if a rock hasn't been changed in terms of folding or overturned by any kind of processes on the planet. So we know that the rock layers down here at the bottom are the oldest, and they will get progressively younger as we go this way. And this younger and older is relative dating. The other type of dating is called absolute dating, and this is a method that's used to determine the exact age in years of a rock or a fossil. And rocks that can be dated like this are mostly igneous, but there's sometimes where we can get metamorphic rocks that can be dated this way. And the reason they both can is because of the what they're made of from the earth. Sedimentary rocks, we're not going to find them dated this way because sedimentary rocks are just made up of a whole bunch of sediment, a whole bunch of broken up pieces of other rock. And if we look over here, we can see this Supai sandstone is 285 million years old. So that would kind of give us an age. Well, that's an excerpt from Imagine Dragons and Radioactive. I thought it was fitting to put it with this piece of notes section. But we're now talking about radioactive decay. And radioactive decay is the method that's used to determine the absolute age of a rock or a fossil. And so as an atom, and we'll get into atoms when we get into chemistry a little bit more, but atoms are the building blocks of everything on Earth. As an atom starts to break down, and that's a term we want to think of, or decay, over time, it begins to lose particles. So what I want you to think about is if we had, let's say, this sounds like a really random example, but we know that squirrels oftentimes don't make it across the road, so that squirrel gets squished. Well, if we go to see that squirrel 1 week from today, it's not going to be what it once was. If we go see it 1 month from today, it's definitely not going to be what it once was. Okay? And that's all it is. That's the radioactive decay. Idea is that it breaks down over time. And each element will decay at a certain rate, and this is known as half-life. So let's go back to half-life and go over that definition one more time. Half-life is the amount of time it takes for something to divide in half. So when we start looking at things on the planet, we will find different elements that make them up and break down over time. And one example of an element is carbon-14. Carbon-14 takes 5,730 years to break down or break in half. So let's imagine I had 100 grams of carbon-14. After 5,730 years, I will only have 50 grams. How much will be left after another 5,730 years? So we started with 100, okay, and that was at time 0. And then we ended up with 50 after 5,730 years had passed. So to get to 20, the next answer would be 25 because that would divide in half. And so our last question is how much total time would have passed. So I need to know what 5,730 plus 5,730 is. So back to that question, here is my 25, but now my answer is 11,460 years. So we started at 100 grams at 0 years, and we went all the way to 25 grams at 11,460 years. So we use half-life to date a rock or a fossil. So we want to see how old. So when you hear about this Tyrannosaurus rex bones is X number of million years old, this process, this half-life process is what is used. And so carbon-14 is often what's going to be used when we think about living or once living things. I shouldn't say living anymore because obviously they're dead, but fossils, bones, and wood. Up to about 75,000 years, we can use carbon-14. After that time, we may have to go and look for other elements that could be present, or also where this fossil may have been found in relation to the rock layers that they're in. The thing to remember is, we all as living organisms start off with a set amount of carbon, and that amount will break down at a constant rate throughout an organism's life, or the end of, after their life is over, I should say. So if we know the end, we can work ourselves backwards to how much was at the beginning. And over here, what I'm pointing at with the arrow, these are just some other half-lives of elements. Please do not feel like you have to know these or memorize these. They just kind of give you an idea, especially if we start thinking about the age of the Earth. We could use, uranium-238, given its half-life being 4.5 billion years. Now on your note sheet, you do have a piece of graph paper, and what I would suggest you doing is, it doesn't have to be an exact replica of this graph, but you do need to make a graph on your note sheet, because oftentimes on the EOG we will see a graph representing half-life. So what this tells me is, I have 100% of something, whatever that is. So it's 100% of it. When I go through one half-life, which means I've divided in half one time, I get to 50. That's my one half-life. And if we were using this 10-gram sample, it would become now 5. When we go through 2 divisions, we're at 25% of our initial amount. And as we can see, from 5, it becomes 2.5, and so on. So please make some kind of similar graph in your notes so that you can look at this graphic representation. Every half-life graph is going to be in this exponential sort of decay format. So when we talk about half-life, we also have to sort of bring in a concept of something called parent and daughter material. And what I want you to think about parent and daughter material is that the parent material is the original element. Okay, that's what we started out with. And that's what started to decay. So as I start off with a parent material of 100%, my daughter material would be at 0%. When I decay that 100% to half, my daughter material now jumps up into the picture and becomes half. And so then, of course, if I go 25%, this is 75%, and obviously when I get to 0, this over here will be at 100. Okay? So what this tells us is, if we know this, if we find a rock and we know the daughter material is at 50%, we know what's connected at that 50%, we can also age the rock. Over here, we see some other pairings of other elements. So for example, potassium would be our parent material, and over time, it would break down into argon, okay? Or we have uranium, and over time, the uranium parent element breaks down into lead. So if I found a certain amount of lead, I could work my way back to the amount of initial uranium, and I could go through and figure out how much time has passed. Now here's the different, or a pictorial way at looking at parent and daughter decaying. So we can see mama right here, and this is that 100%, okay? And mama divides in half, so this is mama at 50%, and here we got this little girl, more like at a 50%. Okay, and so we're gradually breaking this mama down, and of course based on this breakdown, it's not exactly 50% because this won't work out at the end over here, but you kind of get the point. So after time, eventually, if we were to work our way all the way over here, which doesn't exist, we would have no mom and this big daughter taking up the whole thing. Alright, so let's start calculating half-life. And the best way I have ever known to calculating half-life is finding or setting up a chart like this. And we always have time and we have amount. And your time will always be 0 when you start. So please don't forget that. You always have to start at 0. So our question is, how old would a fossil be if it had only 1/8 of its original carbon-14? And we have this reminder that carbon-14 takes 5,730 years to divide in half. So at 0 years, we're at 100% of our amount. Go into the future, 5,730 years. We only have half now. We go 5,730 more years for a total of 11,460 years. We're at a quarter. We go 5,730 more years into the future. So we're going to add that 5,730 to this number right here. And we get 17,190 years, and that will get us 1/8. So to answer our question, how old is our fossil? Our fossil is 17,190 years. All right, so let's try problem number 1. The half-life of radon-222 is 3.8 days. How much of a 100-gram sample is left after 15.2 days? If radon-222, if this number right here messes you up, just scratch it out. We don't need to know about it being radon-222. You just know that radon has a half-life of 3.8 days. That's all you care about. So we can see we start at time 0, and it says how much of a 100-gram sample is left, which means that tells me that 100 grams is what I'm starting with. So I need to take this time down here all the way until I get to 15.2. And whatever it is on this side is going to be my answer. So as I do my math, we can see 0 days. I'm going to add 3.8. Haven't reached my 15.2 yet. Add 3.8 more. I'm at 7.6. Still haven't reached my number. Add 3.8 more. Still haven't reached my number. Add it one more time, and I'm at 15.2. So that is my number. So I need to go 1, 2, 3, 4 more numbers on this side over here. All right, so now let's go ahead and look at it from the other side. So we calculated this side. Now we have to come over here. We have 100, then we got to 50, divide that by 2, get 25, divide that by 2, get 12.5, divided by 2 one more time, and our final answer is 7.25 grams. So on this side right here, all we did was add our half-life to every answer that we got. Over here, all you did was divide each answer by 2. All right, let's look at a second problem. Carbon-14 has a half-life of 5,730 years. So I've said that a couple of times, so hopefully maybe it's kind of not as unfamiliar as it was at the beginning. If a sample contains 70 grams, so that's what we're starting with, how much is left after 17,190 years? So remember, we always start with time 0, and we know we started with 70 grams. So I'm going to have to calculate this side all the way down until I get 17,190 years. And however many times it takes me to get to here is how many times I'm going to use to get the gram amount down at the same point. All right, so we went through and I did the calculations. We started at time 0. Remember, on this side, we add our half-life to each of our answers. Okay, so I added 0 plus 5,730, and that gives me that. I still didn't reach my time yet, so I got to keep going. I take my 5,730 years and add my half-life up here, which is 5,730, so that gives me 11,460. I still haven't reached my end number, so I'm going to add my half-life one more time. So I'm going to take 11,460 and add 5,730, and there is my final answer. So on this side, I'm going to have to divide 70 by 2 here, here, and this will get me my final answer. All right, so now, as we've already gone through and done some of the calculations, we did this side already. Over here, we know we have to fill in this box, and this box. We took 70, remember on this side over here, we divide each number by 2. That's what we do over here. So 70 divided by 2 is 35. 35 divided by 2 is 17.5. 17.5 divided by 2 is 8.25. So my final answer after 17,190 years, my sample will only have 8.25 grams. Alright, so we have one more problem that I'm going to let you calculate on your own, and you're going to bring your answer to class, and your teacher's going to go over this with you, especially if you're not understanding how we got it. So the question is, how much of a 500-gram sample, so that is our starting amount, which is why it is right over here, how much of a 500-gram sample of potassium-42 is left after 62 hours? So that tells me that this bottom number it's probably going to be 62. Okay? The half-life of potassium-42 is 12.4. So what this tells me is on this side, I'm going to add each of my answers, I'm going to add the half-life. So every time 0, I'm going to add 12.4. This answer, I add 12.4. I'm going to keep going until I reach 62. On this side, I'm going to divide each answer by 2. So go ahead, calculate this out. You should be able to answer this question at the next time you see your teacher, and you should be able to tell them how many grams of this potassium-42 is going to be left after 62 hours. So let's go back to those beginning questions that we started off with. If you cannot answer these questions, please make sure you go back and rewatch this video or ask your teacher for clarification, because these are the essential questions on this set of notes. So first, how can the amount of apparent material in a rock sample be determined by using half-life? Remember that parent material is the initial original material that's found. Number 2, how does the amount of parent material in a sample change as time increases? So we should be able to answer that because we calculated problems dealing with that. And the third is, how does age of a rock at the bottom of a rock formation compare to that of a rock at the top of a rock formation? So remember, if you cannot answer these, go back through this presentation or write some questions out and give them to your teacher. Thank you.